has expressed a desire to have posters for the conference, so they were printed out and people are welcome to take it. Oh, you got it. Okay. So I see that people have already taken. All right.
No, this is fine.
So, welcome to the post-tea session.
This is working. Right?
Pleasure
Hello.
to introduce Professor Parthasarathy, formerly of the TIFR, who will speak on classification of irreducible discrete series representations of reductive groups of HC class.
By minimal K type.
By minimal K.
In the Institute for Advanced Study, Professor, I read that Professor Harishchandra, he usually gives seminar there every year, but there were 2 years when he did not give the seminar, I heard. Fortunately, the first time when I went there, there was a seminar, and there was one particular lecture where, and also at the Institute, the usual practice is to have this seminar in 2 parts, and in between they call it a cookie break. So there was one particular lecture when, just when the first part of the lecture ended, I went near Professor Harishchandra and I told him something about the lecture, some another way in which it can be looked at, something like that. I was familiar with that because I had just my thesis work was at that time finished, so I was familiar. So I discussed a point with Professor Harishchandra during the cookie break. So both of us were there in the seminar room and none of us went for the cookies. And when everybody came back, Harishchandra acknowledged and started by explaining what I told him. It was very nice. So I'm very thankful to Harishchandra for all the things he did and which helped me to learn a lot of things. Okay, at the Institute, in my first visit, Professor Hota from Sendai, he had also come and we collaborated at the time, and we proved a characterization of the discrete series by minimal K type, but assuming some hypothesis on the Harishchandra parameter, sufficiently regular, something like that. It just happened that there are many other theorems, for example, geometric realization. So many of these theorems had that assumption at the beginning. Later on, when Blackner's conjecture was proved, many of these assumptions were removed, but this particular characterization by the minimal K type was not looked at all. I mean, it looks like nobody had thought of removing the assumptions. So only a few years back I came to know about this, and then so this talk answers this question of removing those assumptions and proving from all discrete series using Dirac operator methods and using a result of Susana Salamanca Riba, and this is done in the context of groups of Harishchandra class using Mackey's irreducibility criterion also. So as I said, my group G will be of Harishchandra class, but initially I will assume that it is connected. So GE denotes the identity component, but initially, until I come to it, first I will prove for connected groups and then I will discuss the Harishchandra class group. So initially my G will be equal to G, and then there is always this task of defining all the notation involved. So you have this compact torus, compact Cartan subgroup T, maximal compact subgroup K, and corresponding real least subalgebras and their complexifications. Well, I don't know why. So we fix a positive system P, and then that gives rise to positive system for the set of compact roots as well, and we have this Cartan decomposition. The complement of the positive roots, complement of the positive compact roots in the set of positive roots is denoted by Pn, and that is called the set of non-compact positive roots. Any questions about the notation or anything at all? We take a dominant integral, a linear form, and rho denotes half the sum of the positive roots, rho k the same for compact roots, and rho n the same for positive non-compact roots. Then you have this dominant regular integral element by adding rho, and the verb pi lambda, sometimes I will say omega lambda, but it's verb pi lambda, and in the Indian context we sometimes also say omega pi. So that is the irreducible discrete class representation associated to lambda plus rho by Harishchandra. Restricted to K, the representation of K with highest weight lambda plus 2 rho n, that's dominant. Lambda plus 2 rho n is dominant, and restricted to K, that irreducible component occurs. And if mu of some highest weight is of the form lambda plus 2 rho n minus alpha, where alpha belongs to Pn, that will not occur in the discrete series. But now the problem of characterization by the lowest K tab is we don't start with the discrete class representation, we start with an irreducible unitary representation. The assumptions are that this tau lambda plus 2 rho n that occurs in the restriction of the representation pi to K, it occurs, and no highest weight with respect to K is of the form lambda plus 2 rho n minus alpha. That is the assumption, and then we want to conclude that the representation pi is in fact this discrete series representation omega lambda plus rho, or omega, well now I have capital lambda, so omega lambda. So that is the theorem here. Any questions? Sorry? Oh. So let pi be an irreducible unitary representation of G. Suppose that the finite dimensional K representation with highest weight lambda plus 2 rho n occurs in the restriction to K, but nothing lower than that occurs. Okay. Then the representation pi is the same as the discrete series.
You need unitary in this term? You need pi to be unitary?
Yes, yes.
Otherwise it's not true.
Pi is unitary is assumed.
It's false if pi is not unitary?
Well, my proof works when pi is assumed to. I use the Dirac inequality in my proof, and that works when you assume it is unitary. So you have the Killing form, and then you also have the Clifford algebra. The Killing form restricted to P is positive definite. So you have the Clifford algebra. You have the spin representations, and you can the Lie algebra K embeds in SOP by adjoint action, and you can restrict the spin representation, or even you can restrict both the half spin representations to pull back to K via this adjoint map from K to SOP. And it is true that for the two half spin representations, the weights are disjoint, there is no common weight. So one of them is called chi plus, the other one is called chi minus. Oops. Well, here in this screen I describe what are the other weights, how do they look. So you take a subset of Pn, the set of positive non-compact roots. A denotes a subset of Pn, and that bracket A, angular bracket, that denotes the sum of all those roots in that subset. You subtract that from rho n, all the weights are of that form. You can also say that all the weights are of the form minus rho n plus the same quantity A. Okay, so the theorem which was proved with Hota has that condition which is mentioned there at the bottom of the screen. There is a notion of a formal Dirac operator for any irreducible representation. So it goes from the representation space tensor with the spinors to the same space, the representation space of pi tensor with the spinors. So you take an orthonormal basis in P and take the sum pi xi tensor, the Clifford multiplication with respect to xi. That sum is denoted by d pi, and that is called a formal Dirac operator for pi. When you apply the formal Dirac operator to this, we assume that there is this particular K type, that representation space is denoted by W. So you apply that formal Dirac operator to W tensor L, so it's obviously contained in the subspace which you see on the right side. You apply this subspace, the Cartan, the minus one eigenspace for the Cartan involution, that is PC. You apply that to that space W by the representation, given representation pi, a tensor with L. So the Dirac operator, when you apply, it's contained in that. So here's this lemma says that when you tensor the spin module L with that specific irreducible K type which we talked about, in the tensor product, a particular representation of K with highest weight lambda plus rho n that occurs in that tensor product. Can I go to the next slide? Okay. This is a very easy lemma. Well, the assertion of the lemma is, that is only part of the assertion, and in this tensor product W tensor L, in this tensor product, no irreducible constituent has a highest weight of this form, lambda plus 2 rho n minus alpha. Well, wait a moment. Oh yeah, that's this same. The assumption on pi, which I mentioned in the beginning, with those assumptions, we want to conclude that pi is a discrete series representation, omega lambda. So that assumption is stated here again, and then the conclusion is that when you apply the formal Dirac operator to this W tensor L, if if mu is the pk highest weight of an irreducible k submodule, when you apply that formal Dirac operator in that finite dimensional image, so if mu is the highest weight, then that mu cannot be equal to that specific highest weight stated in the, I said that lambda plus rho n, that representation occurs, and so now I'm saying that when you apply the formal Dirac operator, that does not occur here. W stands for the representation space of the finite dimensional irreducible representation of K with highest weight lambda plus 2 rho n. That the assumption was that occurs in H pi, the representation space of pi. So that is W. Okay, so this will mean that before you apply d pi, there was a constituent. You would not see this constituent after you apply d pi. That means that the d pi will be 0 on the subspace. That will be the corollary. But the proof of how do I go back? Right. Typically, the proof of the assertion in this lemma is typically how the Dirac operator inequality is used. What's the Dirac operator inequality? I have not recalled it. It says that if you know that a certain representation is irreducible unitary, and if you know the value of the Casimir operator of G on that representation, then for any irreducible K type in the tensor product of the entire K finite vectors in that pi, tensor with the spin representation L. So for any highest weight psi occurring in the tensor product, if you take psi plus half the sum of the positive root compact roots, that is bounded by, well, the norm of that is bounded by the square root of some expression involving the Casimir operator applied to the representation. It's a simple proof. I mean, it's very easy to prove this Casimir, this Dirac operator inequality applied yields that corollary, or yields that lemma, and then the corollary is a consequence of the lemma. But let's not go through this now. Well, okay, so as I said, this is typically what you, this is typically a step whenever you apply the Dirac inequality. Okay, now, so what is the consequence? So this lambda plus rho n is in the Dirac kernel of pi, and the infinitesimal character of pi is given by the orbit of lambda plus rho. Because of that, that is the so-called Vogan conjecture for whenever you have a representation of G, there is something called Dirac homology, and the Vogan conjecture says if you know a k-type occurring in the Dirac homology, that will tell you what the infinitesimal character is, and that was proved by Pansich and Huang. Okay, so the infinitesimal character of pi is given by that orbit of lambda plus rho. You take all the positive non-compact roots on which lambda vanishes, then theorem proved by Susanna Salamanca-Riba tells you that the set of positive roots P. Oh, I should point out, on the screen. I forgot it all this while. Oh yes. Okay, so that is the set of positive non-compact roots, and with all that information, there is a theta stable parabolic subalgebra Q with that Levy decomposition, for which, well, I guess I shouldn't even, yeah, for which that intersection of positive non-compact roots with the roots in the Levy part is contained in this set. What is this set? This is the set where the lambda is 0. Okay, so, and pi is isomorphic to that cohomologically induced representation AQ lambda. Well, okay, so these are the various avatars for AQ lambda here. So you do some more calculations, and then you conclude that the pi is isomorphic to AQ lambda. Oh, rather, the pi isomorphic to AQ lambda is what you get when you apply the Salamanca-Riba theorem. But the additional calculations will actually tell you that it is isomorphic to the cohomologically induced representation, starting with a Borel subgroup B for the same lambda. Well, that's how you conclude AQ lambda is AB lambda isomorphic to the Borel discrete series. So now we come to the, any questions so far up to this? Any questions?
Yes. Salamanca-Riba's theorem uses the assumption that
Pi was unitary, so that was used to, I used the Dirac inequality in the arguments. So that is where I use pi is unitary. What is your question, please?
is unitarity also an assumption in Salamanca-Riba's?
Yeah, that is an assumption in the statement of that theorem.
Could you say what is the input for the theorem? So what are you using? Unitarity and what are...
Sorry?
When you apply Salamanca-Riba's theorem, what is the input of the theorem? What is the...
When I apply the...
That theorem algebra, what is the input? You have a unit.
The input is that the representation, no, the input is that pi is an irreducible unitary representation. It has that infinitesimal character which was deduced from applying Hogan conjecture, and but that's all the input. All the irreducible unitary representations with that integral infinitesimal character, they're actually an AQ lambda.
So if it has GK cohomology, then it has, sorry, if it has Dirac cohomology, then it has GK cohomology, right? So you could use Hogan-Zuckerman. So you could also use Hogan-Zuckerman.
To conclude that, right out, yeah, you're right. I think the referee pointed it out when my paper was submitted. Okay, now first of all, we have to formulate what will be the statement in the case of groups of Harishchandra class. Okay, so what are the discrete series representations, irreducible discrete series representations in the case of groups of Harishchandra class? So what I want to tell you is that if so in this screen I have only the definition of a group of Harishchandra class. So it has finitely many connected components, and then there is this homomorphism into the inner group of the complex Lie algebra, inner automorphisms. And also that the group G is allowed to have a Lie algebra center, and G1 is G bracket G here. But we assume that the analytic subgroup G1 of the connected component corresponding to the Lie algebra G1 has finite center. So we'll assume that G1 is linear and has a compact Cartan subgroup, and the center of the identity component GE has trivial split component. Okay, the group GE, the split component of the center should be trivial. So yeah, okay, so how do you describe the discrete series for groups of HC class? You take the connected component, you take the connected component, and now take the centralizer in the group, in the Harishchandra class group, you take the centralizer of the connected component, let's call that group B. Yeah, the B is the centralizer of the connected component in G. So when you take BGE, that saturate the connected component G by multiplying it by that group B, so you get an open subgroup. In fact, it will be an open normal subgroup of G. So you start with a discrete class representation of the connected component, and then you take a finite dimensional irreducible representation of B such that the action of the center on one and the action of the center on the other, they have compatibility. Then you can extend to an irreducible representation of that BG. So if you started with an irreducible unitary representation of the connected component, which is in the discrete class, this representation of BGE, by starting with an irreducible finite dimensional representation of B, whose action by the center is whose action by okay, so B is the centralized of the connected component. So certainly B will contain the center of the group G. Okay, the center of the group G will be contained in that B. So the action of C on for the representation coming from B and the action of C for the representation coming from G, they should be compatible. So then when you extend, you get a discrete class representation of that open normal subgroup BGE. From this, when you do induction to all of G, you get a irreducible representation. That is using Mackey's irreducibility criterion. That's what I was saying. Mackey's irreducibility criterion. That needs a proof, but I don't think it's a good idea to get involved with the proof and get lost somewhere. So that is a statement. I can go to the next screen and come back if you want to. Oh yeah, I wanted to also say that you can do the same thing. So how do you describe the maximal compact in this group of Harshchandra class? You take a maximal compact subgroup of this connected component GE and take its normalizer in the Harshchandra class group G. Okay, the normalizer of a maximal compact sitting in the connected component. So that is going to be a maximal compact for G. And then again you have the same description for, this K will, this maximal compact in the Harshchandra class group is going to be disconnected group, but so again you will be in the same situation. So from the connected component G, take the maximal compact there and then take an irreducible representation of K. You can go up to BGE intersected with K. Okay, you can go up to that. That is the same description. The representation of K and the representation of B. The center of G is going to be contained in B. So in the intersection with K, there should be compatibility, and then you extend to an irreducible representation of the maximal compact of G intersected with your the open normal subgroup BG. So take this irreducible representation and induce to, well, that not any, you don't start with any irreducible representation of K intersected GE, but that particular one with highest weight lambda plus 2 rho n. Okay, so when you go to that open normal subgroup and intersect K, that is going to be irreducible. Now you induce to all of K, that will be irreducible again using Mackey's criterion. So now how we want to formulate that analog of that theorem, the original theorem for connected groups. We want to formulate an analog for this Harshchandra class groups. So that is in this screen. And essentially it involves the description I mentioned about constructing a discrete series representation for the group G of Harshchandra class. Yeah, any discrete series representation of G arises in this way by starting with a representation, a discrete series representation of the connected component, and then starting with a compatible representation, irreducible representation of B. So that gives a representation of this open normal subgroup, and then you induce, and that will be an irreducible representation. Any irreducible representation of any irreducible discrete series representation of Harshchandra class arises this way. I think so. There are, you would know many references to for Mackey's irreducibility criterion. So the Mackey's irreducibility criterion in the particular case we are looking at, it'll require, you want to induce a representation, irreducible representation from that open normal subgroup to all of G. So the criterion will say that if you take an element of G which is not in that open normal subgroup, and then you conjugate the representation by that element G, that should not be isomorphic, the representation of that open normal subgroup, irreducible representation of the open normal subgroup. If you know this, then Mackey's irreducibility criterion tells you, guarantees that the induced representation is irreducible. So that is what is proved. That is what is needed to be proved. But I don't think I'm showing you a proof here in this exposition. Same thing for K also, for that particular tau lambda plus 2 rho n. So now what is the analog of that characterization by minimal K type for groups of Harishchandra class? So let pi G be an irreducible unitary representation of G on a Hilbert space, and take the K finite vectors. Suppose there exists an irreducible K submodule script W which is stable under K and it's isomorphic to an irreducible K module of the type we mentioned earlier. Suppose this exists, such a thing exists. Yeah, suppose pi G is an irreducible unitary representation of G. Suppose this analog of tau lambda plus 2 rho n, but for this Harishchandra group. So suppose that exists in this, the representation space, finite dimensional representation space for K. I am denoting by the script W. So this is the assumption. The representation of, we assume, suppose this script T is an irreducible K submodule of PC tensor W. I mean everything considered as a K module. For K is the maximal compact for the Harishchandra class group G. Suppose this script T irreducible. Suppose it does not occur in the discrete series representation of G for the Harishchandra class group. Suppose it does not occur. That is also part of the assumption. Then the conclusion, now what is new here? So nu is the representation of B. Okay. So then the representation pi G is isomorphic to this discrete series. Okay. Any question about? Can I go to the next slide? Okay. So this is, you see that 4.12a, wherever that 4.12 came from. So 4.12a. So that is one analog of that minimal characterization by minimal K type. This is one analog of that. There is a second analog, 4.12b, that is in the next slide. So again we start with the discrete series representation of, we start with any irreducible unitary representation. Oh my God. No, zoom. Whoa. There is no zoom here. Okay. So suppose we start with, let us start with an irreducible unitary representation of G on a Hilbert space H pi G, and this is the K finite vectors. Suppose that there exists an irreducible case, the same assumption as in theorem A, which is isomorphic to this irreducible representation of K we described. We assume if T is an irreducible case about, now the statement about, the assumption about T is different. Earlier it was, well, I have clicked 4 times to go back to the previous screen, but in the earlier screen that part was different. Now, so there we assume that script T is a certain representation which does not occur in that discrete series, but now the assumption is different now. This is more like the theorem without going to Harishchandra closet for the connected group. This assumption is more like this, like that. Well then, the representation is isomorphic to the discrete series. So this is the analog I have. This pretty much said everything I wanted to say briefly. The lecture should be over now, but with the permission of the chair, I want to say some more things if there's a lot of time, I think. Okay, I do not have an analog of this theorem 4.12a or 4.12b for AQ lambda. What I said is for discrete series. I do not have it for cohomologically induced modules, but the original theorem for the connected group for discrete series, characterization of discrete series by minimal k-type for connected real semi-simple Lie group, I have an analog of that for AQ lambda. So this is, okay, so there is an analog of that for AQ lambda. All this is, has appeared and, yeah, all this has appeared in, I think I have a reference to where it appeared, Electronic Journal of Representation Theory of the AMS. Okay, so now I want to go to a different, I mean, whatever I said in the abstract from my talk, which is, so that's all over. I mean, so the first part of my talk is over. I want to go back to a talk gave on the 70th birthday celebration of Harishchandra 30 years ago. So so at the time I talked about coherent continuation of a coherent family and define analog of the coherent family for quantum subgroups at roots of 1. So at the time I had a proof for some low rank cases. That is what I talked about in that Harishchandra conference. And I made some conjecture there that without any case by case consideration, I mean, the formula, the quantum analog was given. It was described. It is an algebraic expression, but there was no way that one could prove that that is positive, that they're actually honest, actual representation, not just virtual representations, but actual representations on a positive cone. That was not available, but in low rank cases it was available. And later I proved for discrete series a few years later, and some more low rank cases, including G2. I had even forgotten that I proved it for G2. And also for SL4, SL4 rank 3. I had proved it for those. But that's how all that happened within those 3 or 4 years after the Harishchandra conference here, 70th birthday, but that conjecture still remains, and I don't want it to go to the oblivion. Some young people here would perhaps be interested and take it up. So suppose that you have a coherent family of virtual modules parameterized by a translate of a lattice, assume that the members of this family are dominant parameters or actual modules, not just virtual modules, but the whole thing on every point of a lattice need not be actual module only, it will only be a virtual module. Then you can define the quantum analogues of this family for quantum groups at roots of 1 as a coherent family of virtual modules. It involves an algebraic expression. So this is the conference 30 years ago. Okay, some low rank cases it was proved for discrete series, it was proved for all groups whenever discrete series exists. And I have a web page, but that doesn't seem to work now because TIFR changed for security reasons, they changed it. I think Arvind Nair promised that when he goes back he will set it right, or rather take the administrators and set it right. But you could still access, if anybody is interested, from my ResearchGate page. Most of my publications will be there, and including these four publications about these quantum analogues. By the way, the low rank cases, and for this, it uses quantum analog of, Lustig considered this quantum analog represent finite dimensional irreducible representations of the complex semisimple Lie algebra over G, complex semisimple Lie algebra G over C for all the finite dimensional irreducible. Lustig considered quantum analogs and then specialized to quantum analogs at roots of 1. And for those modules, they won't be irreducible, but he described what are all the irreducible components, which he gave explicit description. What are all the irreducible components occurring there? And my proof in the low rank cases uses that description. Well, again, this part is over. Do I have 5 more minutes? Yeah? Okay. In my first lecture on the 9th, I made some remark about, if all the orbital integrals for a cusp form, let me not be precise, but afterwards I'll be precise, but if all the orbital integrals for all the Cartan subgroups are 0, then the function is 0. But there was some assumption and there was some confusion about that remark, without bearing in mind that there was some assumption. So I just want to clarify that. So we were in the middle of a discussion that if there is a non-zero cusp form, then there is a compact Cartan subgroup. The group has a compact Cartan. We were in the middle of that discussion, and I made an assertion that if all the orbital, I started with this non-zero function f cusp form, and I said that if all the orbital integrals are 0, then the function is 0. But you see, f is a cusp form, so all the translates of f, all the right translates, left translates, all the translates will also be cusp forms. And if there is no compact Cartans, then all the orbital integrals will therefore be 0, because for a cusp form, the orbital integrals on non-compact groups are 0. And so you have a relation like this for the fundamental Cartan, which is now non-compact, if G has no compact Cartan. So you have a relation like this, and you can apply this relation also to the translate of f. You can apply also to the translate. So that is what you need to conclude that f is 0. Okay, I'm done. Thank you. Any?
Any questions?
Could you say 2 words about what this finite group B can look like?
Okay, B is the centralizer of the connected component. So first of all, we allowed the connected component to have connected center, but then split component should be trivial. So the center of the connected component can have a non-trivial torus. So B need not be finite, but okay. So the question is modulo this center of G0, what does it look like? Okay. Well, there could be, it could be a permutation group, but it could be sitting there, you know that.
Any other questions? Yeah, question.
Can you pass him mic to him? Can you please talk louder and yeah, there is, you can talk in the mic. I didn't bring my hearing aid because it has all that has to pass through security check in the airport, and somebody may put a heavy bag on this hearing aid, so I didn't bring it at all.
Does this classification extend to limits of discrete series if lambda plus rho is not sufficiently regular? I mean,
Oh, the original.
no, yeah, the first part of the classification of representation by many
Oh,
type.
the first part, assuming the Dirichlet class group is actually connected.
Yeah.
Yeah, in that case, oh, okay, now I'm getting confused with my quantum analog paper. So, okay,
For limit of discrete series, you have like lambda plus rho maybe.
my assumption, well, the Salamanca Reba, I don't know what she, or even Wogan Zuckerman, maybe Wogan Zuckerman can come to the help and say it for limits of discrete series also. But I don't think Salamanca Reba was there. Concerned only with when the representation is unitary, irreducible unitary, and when the infinitesimal character is regular, non-singular. Maybe also, but I don't remember now. But that is the place to look, Wogan Zuckerman and Salamanca Reba.
So when it's the discrete series, it only occurs coherent, it doesn't occur in GK.
Oh, yeah, so can you give the mic to him also?
I could be wrong, but you make it look like you're using GK cohomology at some point in the
Instead of using,
in the
sorry?
limit of discrete series, they don't occur in GK cohomology.
Discrete series has GK cohomology. Yeah?
Limits of discrete series,
Limits of discrete series.
they don't occur in GK cohomology.
Now my feeling is that they have, I mean, the tau lambda plus 2 rho n, that if you add rho k, there will be lambda plus rho, lambda plus rho, but we don't know if lambda plus rho is regular. Okay, lambda plus rho may be singular on a non-compact group. So it's some.
Maybe you don't explicitly use GK cohomology in your proof. In your proof of discrete series, maybe you don't use the fact that they are in GK cohomology.
They are in GK cohomology, or maybe let me come near. Just. Excuse me, yeah.
In your proof, you don't use the fact that discrete series contributes to GK cohomology?
No,
When you use
The,
Salamanca,
so before we used Salamanca-Riba's result, all that we derived was that it is an irreducible unitary, no, from the assumptions of the theorem, it is an irreducible unitary representation which has integral infinitesimal character, and that is regular. That is where we came up to, and then used Salamanca-Riba. So it was limits of, no, I didn't look at limits of discrete series in that discussion at all.
So, any other questions? Okay, if there are no further questions, let's thank the speaker. So we'll reassemble in 5 minutes for the final lecture of the session.